much like an entrance. There's two types of grading couplers that exist right now. One is called an angle grading coupler, and the other is a vertical coupler. An angle grading coupler is commercially available, and it's optimal when the light source hits at it at an angle. A vertical coupler is a really novel design created by the grad students in Professor Connie Chang Hassanein's group. So it hasn't been fabricated and it isn't commercially available. And the vertical coupler also uses high contrast gratings to couple light very efficiently inside the chip. So as you can see in these pictures, in the angle grating coupler, these gratings are within the surface of the plane, while these are above the plane and are surrounded by a material with a low index of refraction. And these gratings itself have a high index of refraction, which brings about the contrast. This gap is really important because this is how the light gets coupled inside. A waveguide is another part in integrating light inside the circuit. It's comparable to a wire carrying electricity, but a waveguide carries light. And the waveguide has a high index of refraction, so using total internal reflection, the light propagates through, as you can see in this picture. And all of the waveguides that are in my project are silicon on insulator waveguides, which means that the waveguide's made out of silicon and it lies on top of an insulator, and in my case, silicon dioxide. So the main motivation for my project is to use optics integrated with circuitry. So this allows for fast transmission of information and higher efficiency, as well as a compact design. And so as you can see in the picture, for an angle grating coupler, the light source needs to be at an angle for it to be to couple light optimally, while in a vertical coupler, it can be straight and it's planar to the chip, which is easy to fabricate. And so this is a schematic of the vertical coupler that I optimized. As you can see right here, this is the light source, which is vertically falling on the grating. This is the silicon grating. This is a silicon dioxide gap right here, and this is the silicon waveguide. Here is the silicon dioxide again. So since the waveguide is sandwiched between two material with a low index of refraction, that's how the total internal reflection works. So to run my simulations, I use three types of software. One of them is called G-Solver. G-Solver simulates gratings by asking for parameters and creating it in the software itself. It also allows me to sweep different variables, which means changing variables to see how the output results. And another thing about G-Solver is that it's uniform and periodic, which means that all of the grading bars have to be the same distance apart, and it's periodic since it's an infinite grading. And the really good thing about G-Solver is that it's used specifically for gratings, which makes it really user-friendly. And here is a picture of how G-Solver looks like. So you can see I would just have to input all of this information and it'll give me a model of my grading. So here's a really nice looking plot used from the data from G-Solver, which I plotted in MATLAB. And as you can see right here, it's a grading thickness versus wavelength plot. And these lines are resonances that are created from the high contrast gratings. And when this curved line seems like it's going to repel this vertical line, it shows that there's optimal, the coupler can couple light very efficiently. And using simulations, I found out that the optimal thickness of the grating for the schematic shown above is 0.95 microns. So Lumerical is another simulation software that I use that uses finite difference time domain technology to simulate its gratings. It can simulate gratings, and it can simulate other types of applications like solar cells and other things, and it allows me to build my grating rather than give in some parameters and make it for me. But with this complexity, with all of these features, it also brings about complexity, and it does take some time to run these simulations. And here's a plot that, using the data generated from Lumerical, I solved in MATLAB. And here we can see that this area has a very high efficiency, which leads me to believe that a gap thickness of 0.29 microns would be most efficient. And here's just a diagram of how the coupler looks in numerical. So, and here are the optimal results that I found, and all of these results comply within feasibility of fabrication. So this type of coupler can be built. And here is a movie which looks really cool. Let's see if I can play it. Well, if not, I can show you right after. So what happens is light comes in from above, it comes into this grating, and it couples into this waveguide. So half the light comes on the left and half the light comes on the right.
If you exit the presentation, can you play it?
Yeah, maybe.
If you do just escape and see if you can, there's a play button somewhere.
Is
it computer fine or is it?
No, the computer's fine.
I think that happened to us yesterday during rehearsal too, right?
projector froze?
The projector froze when we were playing the FTDT
Oh, really?
video, but and not this presentation. It was Vincent's.
Okay.
Vincent, you,
Let's see.
But the computer is okay, huh?
Yeah, the computer's
so you have to disconnect the projector and connect it back again. That's what
Wow.
made it work for us.
okay. Oh, I think it came back to the same.
You can try clicking
Try
it.
clicking it.
Yeah. Or let me see if I can.
Oh, this that doesn't work.
Yeah, physically click it.
Yeah, right now it's not in. Okay, let me exit my presentation. Ah, I'll start after that slide. Okay, so the second part of my project is testing the loss in waveguide systems. So as I mentioned before, the waveguide carries the light that gets to propagate inside the chip. So I measured to see how the length of taper affects the efficiency of the light that actually gets coupled through. And since the chip that I tested on doesn't have a vertical coupler, because they haven't been fabricated yet, it has an angular coupler, I was also able to see the differences between an angular coupler and a vertical coupler design. And I actually simulated the angular coupler on Blumerical, and I found out that it has a much lower efficiency than the one for the vertical coupler that I simulated. The angular coupler, grating coupler, had an optimal efficiency of around 45%, while the vertical coupler design had one of 91%. So we can see a big difference there. And so here's just a picture of the waveguides inside the chip. So these are some patterns that can be tested, but I mainly focused on these straight waveguide patterns that had different lengths of taper. So here's my setup. So as you can see, here is an IR camera. It allows me to view the light that comes in. This is a light microscope. Here's another microscope so I can see the fibers from a different angle. Here are translational stages. The fibers are on the translational stages, and I can use the knobs that have micron movement to move the fibers so they can couple. And here's a picture of what it looks inside, because it's kind of hard to see in this picture. These are fiber holders right here, and these are the fibers, and the shiny like rainbow is the chip. And so so how it works is that light is inputted from one fiber, it goes through the waveguide, and it gets outputted out of the other one, and the other side it has a detector which you can see the power. And here's just a graph of how the angular coupler efficiency was. And here are my experimental results. So as you can see, as the waveguide as the waveguide length increases, that means there's a more aggressive taper. The power, there's an increased loss in power and decreased power output. And here's just a graph showing that. And looking at this graph, I believe this point may be an outlier because it doesn't conform with the other points. And here's a really in-depth picture of what we're looking at. These are the fibers. I took this from inside the microscope. And so the core of this fiber is actually around 10 microns thick. So you can imagine how hard it is to actually couple light in this way. And so just to summarize, a vertical coupler is really efficient, and it has high efficiency and has a lot of promising results through the simulations to couple light, and can be a really good way to further the photonics industry. And for the experimental results, we found a lot of loss in the system in general, but we were not sure, like some of it may be the waveguide, but we're thinking that most of it, there's so many other factors that can contribute to the loss. For example, if the fibers aren't cut vertically with the diamond cutters precisely, a lot of light scatters, and that is also a major factor. And also the coupling efficiency is also a huge factor, because we saw the angled coupler only has efficiency of 45%, so that would also be contributing to loss. So future research would be to see if we can actually fabricate the vertical coupler and test it in real life, and also to test other waveguide patterns and figure out the actual causes of loss and seeing how to reduce the loss. I'd like to acknowledge my mentors, the SHARP program, for giving me such a good opportunity to do research. I really had a great time, and I wouldn't have been able to do this research or anything without their help and have this experience. Are there any questions?
So the table where you had the power loss,
Yeah.
what would be considered a high dB loss and what would be considered a low dB loss?
So a low dB loss it would depend on the initial loss in the fiber. So for example, when we hooked up the fiber directly to the detector, we found that there was already 1 dB of loss. So basically, a good dB loss would be maybe 1 dB above the initial loss of the coupler. So right now, this is pretty bad. Yeah.
In your MATLAB plot, how did you find the optimal data points?
Okay, so in the MATLAB plot, what it is that when I get data from Lumerical, it gives me all the data from the sweeps. It puts it into arrays. So what I do is I read the optimal efficiency in the array in MATLAB, and I see the corresponding points of, like, in this case, angle that corresponds to the highest efficiency. Yeah, Aaron?
In one of your plots, I think it was an efficiency plot, you have 2 vertical lines that are starting to repel.
Yes.
Can you say a little bit about why that signifies optimal coupling?
Yeah, so basically it signifies optical coupling because what's actually happening is that this line it starts at 1.55 microns of a wavelength, and so this line, what's actually, I guess when it's, right now this is a 91% efficiency, but when it's higher, like maybe 97, these lines actually meet where this line comes out this way, and this line comes out this way, so they like collide, and so that is optimal because we see that it resonates at the wavelength that we want. Yeah.
Do you think you can play the movie that was?
Oh yeah. Yeah, I totally forgot. It looks really, really good. Oh. No. When I exit PowerPoint, it doesn't show this.
Do you have it as a separate file?
Yeah. But right now, I think this became the main monitor, so I didn't even see the start menu. Does someone know how to get this out of the two-screen mode? Like a shortcut to it? Okay.
It happened yesterday. I think the final fight, man.
No projector plugged in out.
No, it's not.
Okay. Seen this before.
Vincent has the same final fight. That's gonna happen to him too. So he's gonna, at least he has a few hours to figure it out, right?
Yeah.
Remember this when you're watching your Windows commercials on TV.
And now it's back here.
Oh, it's not. Or actually, yeah, yeah. And it's this one.
This one?
No, the one right. The other one is kind of weird. Yeah, that's what happened.
Let's see if I can back it over here and then click it. And it's not. And that doesn't work.
Or do you want to open it from Windows Studio Code?
What's it called?
My vertical console. Or 10.
Control O.
Oh, it's in my USB too. Or not.
Control O. Control O?
Oh. Okay. Oh.
Okay.
Under computer.
It's hard to navigate like this.
And yeah.
Yeah.
Oh, okay. Yeah. Okay. So, you can see the light coming in from the vertical light source, and then the light gets in the HCG, and you can see it resonating too. And then half of the light propagates to the left, and half the light propagates to the right.
Woo!
Hey, great.
Yeah.
All right.
Yeah, that was worth it.
Worth the wait.
Yeah. And so this simulation actually runs until there's like 0.000% of the light in, so I'm going to stop it right now because nothing interesting is going to happen.
Hopefully, huh?
Great.
Oh, yeah.
Thank you very much.
Yeah.
Okay.